In this bonus video, I'm going to be talking about how to determine the sample size for a hypothesis test using type 2 error. The main reason although the calculations are pretty straightforward as you are going to see, the reason why I didn't include this topic in the lectures, but I put it as a bonus lecture, is because this concept, determining sample size by using some probability calculations or using charts that I'm going to be talking about, is pretty much related with the concept of effect size. And to understand, to appreciate the concept of effect size, I believe students should be a little bit related, or should have some experience related with these kind of experimental studies related with hypothesis tests. So without that experience, I don't think that appreciation of the effect size will be that much useful, I may say. So I just excluded this topic from the whole syllabus of the course, I may say. So anyway, so the idea is, as I said, pretty much simple. Let's say that we have the following typical hypothesis test. Again, our assumption is X is normal distributed, and let's say that sigma square is given. So we are talking about the unrealistic, but the most easy case. So in this case, the test statistic will be equal to X bar minus mu 0 divided by standard deviation normalized by square root of n. So now this is, let's say, as the experimenter or as the statistician that you are going to do. On the other hand, some person actually knows that, but you do not know that the real process mean, population mean, is equal to this mu 0 value, the hypothesized value, non-hypothesized value, plus some delta value. Now, note that still the analyst, let me say, since the analyst, that is you, still thinks that H0 is true, but note that that other person knows that actually this is the case. The only confusion about this analysis probably comes from these change of perspectives. You, the person who does the computations, will assume that H0 is true because it is the usual procedure. Assume that H0 is true, then continue with the whole thing. But during this procedure, we are going to be including this, also this given data, or not given data, but the population mean value, the true value of population mean. So since this is actually the true, the Z0 value will be still calculated using this equation. Nothing fancier. Now, at this point, what I do is, in order to include this information somehow here to see how Z0 will change, what's going to happen to Z0, what are the typical Z0 values that we are going to include, what I'm going to do is, I'm going to add a delta term and subtract a delta term. So what I do is, I put a delta term here, and I subtract also the same delta term. So this is going to be delta standard deviation. Note that still it's the very same value, but I added the same value. I think this should be plus, yes. Minus delta over square root over standard deviation square root of n, the same term here. Now note that, now call this Z1. Now, at this point, although you, the experimenter, are using this procedure, think about that part as that guy who knows the ultimate truth about the whole thing. So you do this calculation, and that guy in parallel has been also doing this. He or she is just going to imitate what you are doing. But instead of mu 0, this plus and minus, the same term is put here. So the same final answer, the same numerical answer is obtained, but it's partitioned into two terms. Now, actually, that guy knows that since this is the true mu value, the X bar, which is going to be sampled from this population, the expected value of X bar indeed is going to be equal to mu 0 plus delta. Hence, and standard deviation of, note that variance of X bar is still square over n term. Therefore, actually, this Z1 is normal distributed with 0 mean and 1 standard deviation. But this part, as I said, let's put it that way, you do not know this part, that other person is knowing this. So let's keep on with the analysis. Here there's a constant. Call it C for the time being. Therefore, what we call as Z0 is going to be a normal distributed Z1 plus C. Again, that person continues with calculations. Now, we know the distribution of Z1. Can we determine the distribution of Z0? Yes, we can. Actually, if you take the expected values of both sides, expected value of Z0 is going to be, this is going to be 0. This is going to be a constant. So this is going to be, and that constant is going to be square root of n delta over standard deviation. And variance of Z0 is going to be equal to, since this is constant, it's going to be simply equal to Z1, which is going to be equal to 1. And note that this is a linear combination of Z1, just as constant is added. Therefore, Z0 is going to be still normal distributed, but it's not going to be around 0. It's going to be around this value with 1 standard deviation. Now, that's the pretty much interesting point here. Now, let's continue with this approach. So in reality, what we are going to do is, in the next step, we are going to be comparing the Z0 value with Z alpha over 2. Actually, we are going to be checking whether compare Z0 with Z alpha over 2. This is exactly what we are going to do. And this person who knows the ultimate truth from his or her perspective, this is actually what's happening. We now have a Z0 distribution. Our statistic is going to have this distribution. So he knows that this is going to be around that expected value, which is going to be equal to square root of n delta over sigma. And the comparison will be between minus and plus Z alpha over 2. And let's assume that it's Z alpha over 2 is here and minus Z alpha over 2 is here. Note that this Z alpha over here 2 can be easily here. That's not going to change anything. So now the question is this: when is this test going to give an incorrect answer? So what is the correct answer here? The correct answer here is actually mu is not equal to mu 0 should be the answer, right? On the other hand, if Z0 comes out to be between Z alpha over 2 and minus Z alpha over 2, then H0 will not be rejected. Note that again, I write this from my perspective, from the analyst perspective, because the other actual guy knows that actually this is the correct form. This is the false hypothesis. Okay, now we are going to find the probability that this is going to occur, because if this, the probability of occurrence of this is what we call type 2 error. So we are interested in type 2 error, which is shown with beta, where the probability is going to be this case. Let's put also an equal Z alpha over 2. All right, now let's again come to this point. Since actual distribution of Z0 is this one, right? So this is going to be the distribution of Z0. So we are interested, actually, let me show it with another color, is going to be this area here. This is the area that we are interested in. So now what is the area here? Note that the analyst can only come up with this result. He cannot go further without knowing the Z0 value, sampled value. But on the other hand, this guy knows the ultimate truth about the distribution. So he should be able to calculate this, because it's just a normal distribution. And below this normal distribution, we would like to find the area between these 2 points. So basically what we are going to do is we are going to standardize this Z0. You may say that isn't Z0 is already standardized? No, Z0 is when A0 is equal, A0 is the true hypothesis when mu is equal to mu0. Yes, Z0 is, we assume that it's going to be standardized. On the other hand, the true distribution is not, does not have mu is equal to mu0 parameter value. It's equal to this one. Therefore, Z0 is not a does not have a standard normal distribution, right? As you can see, its distribution, the population mean is non-zero. So what we are going to do is we are going to subtract Z0. We are going to subtract square root of n delta over the standard deviation from Z1 to standardize this. Now call this Z prime as a standard normal distribution. Now this is going to be Z0 mean one standard deviation distribution. Basically what we very simply do is wherever you have a Z0 value, let's say it's here, just subtract it from this value. What you practically do is you bring the origin or the horizontal y-axis here. This is actually what you do by doing that operation. So this point is going to be 0. What about this point? This point is going to be the difference between two with minus sign. So basically what we simply do is instead of Z0, we are going to be putting these values here. Z alpha over 2 and minus Z alpha over 2. So Z prime, so we can write this as probability is going to be equal to minus Z alpha over 2 minus square root of n delta sigma smaller equal Z0, which I'm sorry, Z prime, standardized normal distribution variable, alpha over 2 minus and delta sigma. This is going to be equal to beta type 2 error probability. And this is going to be equal to, let's continue, this is going to be now, this is standard normal distribution, right? So it's going to be equal to the cumulative distribution function evaluated at Z alpha over 2 minus square root of n delta standard deviation minus this value again, Z minus Z alpha over 2 minus square root of n delta standard deviation value. Now this value here, now think about here as the origin, that minus Z alpha over 2 is usually a small value. If you think about that case here, two-sided distribution is here. Now when mean is here shifted here, so this axis is shifted here, note that this value is going to be even much more negative, actually, where we have this additional component to make it even more negative. What I would like to say is this value is going to be usually very small, so you can assume that this is going to be approximately equal to 0. So we come up with a very simple result where we have this expression. Now this, by using this expression, you can easily find the type 2 error, but there is more to that. Now note that this is the cumulative distribution function value. Now forget about all these type 1, type 2 errors. Basically this means that, think about like that, we have cumulative distribution of, let's say y. It means we have a standard normal distribution here, right? This means if y is smaller than y value for y normal distributed. Therefore, we are talking about a point here with an area equal to this one. So the very same thing we are talking here, basically we are going to be talking about, we have standard normal distribution, we are talking about a point Z alpha over 2 minus this thing, I don't need to write it again. So it's going to be equal to, this whole thing is going to be actually here such that this area is going to be equal to beta. Now here is the point. Up to this point, we are using this Z alpha over 2 or alpha representation as the right-hand side tail area. So this is Z alpha over 2. This is minus Z alpha over 2. If these are actually equal to alpha over 2, or if you take it as alpha, right? If this is Z alpha with an area here equal to this one, minus Z alpha is going to mean that we have this tail equal to area, which is equal to alpha. So what I would like to say is that since this representation has been already used, we use the same thing that is used here. We write here minus z beta. So it's going to mean the z value with a tail, right-hand tail, equal to beta probability, but we are going to take the negative of that now. Therefore, this term inside the cumulative distribution function is going to be equal to minus z beta. So it's going to be minus z beta is going to be equal to z alpha over 2 minus square root of n. I'm sorry, it's going to be standard deviation. Let me get rid of this one. Now what I'm going to do is I'm going to leave n on one side and put all of the rest of the terms on one side. So put this one here, put this one is going to be square root of n delta. Standard deviation is going to be z alpha over 2 plus z beta. And let's go one step further. This is going to be z alpha over 2 plus z beta. I'm going to divide this by this term. And when you square all of the terms, actually, I don't need this. And I don't need this. Ah, no. Ah, yes, I don't need this. Oops. This is the sample size. So what does that mean? This is actually a very useful rule. Now you can, at the very beginning of the experiment, we can agree on an alpha value. We are going to conduct a two-sided experiment, two-sided hypothesis test. What should be the type 1 error that we are going to agree on? Let's say this is going to be 0.05. So alpha over 2 is going to be 0.025. You find the z 0.025 value, you put it here. And then, now the important point. Now, this is the reason why I left it in this case, in this manner is, I'm going to call this effect size. There is a special meaning related to that. Actually, that's the only reason why I do not include this in the formal path of the topics or the route that I followed in a hypothesis test. So I didn't include that in your exams, I may say. So the effect size is that delta is, let's remember what this delta is. That delta is the difference between the hypothesized value and the true value. So there is that much of difference. Let's say if we are talking about, I think the example that I'm going to be talking about is from your textbook. It says mu is equal to, mu zero value is equal to 50 some units, but the actual value is 51. Therefore, delta is going to be equal to 1. So the difference between the hypothesized value and the true value. Okay, that probably means something. But what is the meaning when we divide it by standard deviation? Note that this term is going to depend on the unit of x. So actually the unit of delta is going to be equal to, so let me write it that way, unit of delta is going to be equal to unit of x. Whatever am I measuring? If I'm measuring meters, then it's going to be meters or kilograms or whatever. It's going to be the same unit. And this is something I said about units before. We do not like those units when we would like in statistics that much. And for this reason, we prefer to normalize. For instance, correlation is a normalized measure of covariance. Why we would like that? Because when you say there is a difference of 1 meter, we do not know between the hypothesized and the true value. We do not know without some acquaintance with the data or acquaintance with the process. We do not know whether that 1 meter is a large magnitude or not. Now, when you divide it, the standard deviation, which shows the scatter or the width of the data, this is going to give us an idea about this width. For instance, if the standard deviation is 0.1 meter and we have a 1 meter of difference, then this ratio is going to be equal to 10. 10 standard deviation difference is a huge number. So just to give you an intuition, this is usually used in psychology. This value being smaller than 0.2 is actually taken as a small effect size. When this is around 0.5, we have a moderate effect size. When this is greater than 0.8, we have a large effect size. So this effect size is actually the difference between the actual, and I will try to explain later why we call it effect size. This effect is related with the actually two population cases. We apply a treatment, and when we apply that treatment, compared to the reference case, which has a population mean of mu0, the population mean will change by a unit of delta. But we normalize it with the standard deviation of the population, so that we would like to see how much do we have a change, do we have a normalized change. But as I said, these are usually related with psychology, but a similar case, somewhat a similar case, is can be stated also for statistical process control. Usually 0.5 change is a somewhat significant, while 1.0 change is a pretty significant change in the population. Anyway, so this n value is going to, where was I at the end? We first define this one, right? Agree on this value. Then we just would like to think about the smallest significance change we would be interested. So let's say that we would like to determine a change of 0.5. We are not interested in smaller changes, but we are very much interested if there is a change of 0.5 effect size, then we would like to detect this. Then that beta value is going to be is going to be related with the beta value. So we really would like to detect this. Means that, for instance, we would like a beta value of 0.10. So which means if there is that much of an effect size here, that delta of difference of mu here, so if mu is actually equal to mu0 plus delta, and here delta is going to be equal to 0.5 sigma, we would like to detect it for 90% of times, because power is going to be equal to 1 minus theta is going to be 0.90. So therefore beta is equal to 0.10. So we find that beta value is going to be actually equal to 1.64 or 65, if I recall correctly, because actually it means it is the Z beta value here is going to be this right hand side area is going to be equal to 0.10. So what we do is we add those two values and divide by the sample size. So basically it's going to be, for instance, if alpha is equal to this one, this was 1.96 plus, if this is the power that we would like, if there is a shift of 0.5 units in 0.5 sigma units in population mean, we would like to detect it. Therefore this is going to be 1.96, and this is going to be divided by 0.5, and we take the square here. This is going to be the smallest sample size required to obtain such a power at the given type 1 error case. So the result is going to be, let me try to compute here, 1.96 plus 1.65, all right, 0.05 square. The sample size should be equal to 52.12, and since this is the minimum sample size, therefore, and this should be an integer, we need a sample size of 53 to determine this much of change in mu value. So this part is actually related with real experimenting. So because here at this point, we should have some knowledge, pretty much thorough knowledge about the experiment, about the process, so that we can decide how much of a shift should be detected, the smallest amount of shift that we would like to detect. And if this power is not sufficient, right, 90%, let's say that we would like a 95% here. right? So if this is the case, by the way, I think this was maybe 95%. I cannot remember. Maybe I messed up with the 1.65 value. So anyway, whatever the value that Z 0.10 is, you can find from your textbook. You can put it here. So for any power value and for any type 2 error probability and type 1 error probability, you can come up with the required sample size. Once now you decide, note that these are all before the experiment. Once you determine the sample size, you take that many number of random observations. Then from now on, you construct your hypothesis test. You employ your hypothesis test, the upper and lower critical values, p-value, confidence intervals, all those calculations. So this formulation is one way to obtain the sample size. Now I would like to solve a question from your textbook. Let's say that we have a rocket propellant, and the rocket, this rocket specification required that the mean burning rate should be equal to 50 centimeters per second. All right, and so H0 null hypothesis, this one, and this is our alternative hypothesis. So it's simply, we would like to check, we would like to test whether our rocket propellant suits the specifications or not. Let's say that we are going to conduct this test at an alpha value of 0.05, and sigma is given to us as 2 centimeters per second. So now the question is this: we would like to conduct a test, but we do not know the sampling size here. What should be the sample size? So in order to determine the sample size, we also need to determine also the power of this test at a certain effect size. So at this point, we should be familiar with the experiment, with the rocket propellant, with all the things related with that scenario. We should deem a significant difference. I do not mean here statistical significance, which is related with type 1 error with the boundaries, but it is a significance related with this experiment with rocket propellant. So what is the significant value of the difference from this suggested population mean value that we would like to detect? For instance, if mu is equal to 50.01 centimeters per second actually, do we really would like to detect a deviation of 0.01 centimeters per second? So this question can only be answered on an experimental basis. This has got nothing to do with statistics. So what is that delta value that we need to specify so that we would like to determine that delta value of deviation from the mean value? Just for the sake of this question, we are going to say that we would like to determine a delta value of 1 centimeter per second. So in our hypothesis test, in our sample, we would like to detect a deviation in sample mean when it's at least equal to 1 centimeter per second. If it's greater than 1 centimeter per second, we of course would like to detect this. But if it's at least 1 centimeter per second, we would like to detect that. So now the second thing that we should answer is, well, of course, it's going to be impossible to detect this change with 100 probability, because actually that would mean that the type 2 is equal to 0% probability or 0 probability, which is impossible because we are always going to have some type 1 and type 2 probabilities. So we need a plausible value. For these cases, just like taking the alpha value as 0.05, usually taking a type 2 error probability as 0.10 is pretty much sufficient. So for this case, power of this test is going to be 0.90, which I repeat would mean in 90% of the cases, in 90% of the samples that we are going to take from this population, with at least 1 centimeter per second deviation is mean value, we are going to determine that H0 is false. I repeat again, out of 100 or actually 90% of the samples that we are going to be taking from the population of shifted mean of at least 1 centimeter per second, we are going to, or actually exactly 1 centimeter per second. If it's more than 1 centimeter per second, then we are going to, the power is going to be increasing. But if the shift in mean is 1 centimeter per second, in 90% of the times, we are going to be detecting this. So basically what we are going to do is we are going to go back and use this very simple equation that we have derived before, this one here. All right, can I copy here? No, unfortunately, no, it takes some practice to do that. Anyway, let me put it here. N is going to be equal to Z alpha over 2 plus Z beta divided by effect size square. So Z alpha over 2 is going to be 0.05. Since the two-sided hypothesis, I said that this is 1.96, and Z beta is going to be equal to 0.10 here. This time I'm going to use the normal distribution table and come up with the correct result. It's going to be equal to, the probability is equal to 0.10 is, let's see, it should be something like 1.29. Yes, I hope that's better. Something like this, 1.29. Anyway, so we are going to add these numbers until, let's say, divided by, and this value is, as we said, it is, we would like to detect this much of a perturbation in population mean. Therefore, it's going to be 1 over 2, a 0.5 of perturbation with respect to the standard deviation of population standard deviation. So N is going to be, actually, we can say that greater or equal this value, because this is going to be probably an real number, not an integer. So it's going to be plus 1.28. All right, times 2, and I square it to 41.99, which is going to be 41.99. So we need a sample size of at least 42 observations. Now, the same answer can be determined operation characteristic curves. So these operation characteristic curves here with this D will be this value here, effect size. And this is going to be probability of accepting H0. Note that effect size means there is a difference in population means. On the other hand, this one accepting H0 is actually not rejecting H0, it should be. This means that we say that there is no change in mu values. Therefore, we assume or we conclude that D is equal to 0. So this is the incorrect conclusion. Therefore, this is basically type 2 error. So what we do is at a specific effect size, and here this is going to be equal to 0.5 that we are interested in, right? And these are, note that for 0.05 alpha values for two-sided normal test, which is exactly the case we are talking about. So for 0.05, you can actually draw a line like this. Is 0.5 here? Yes, I think this is 0.5, by the way. All right, if we can bring this down here. So we would like our type 2 error probability equal to 0.10, which is going to be somewhere here. All right, so the point that we are talking about is going to be here. So can I erase these? Let me see. I seem to do that. Yes. So the point that I'm talking about is here, which is, as you can see, about 40. So this graph will give you identical result. Well, actually, this graph is as you can see, is very practical. Unfortunately, you have only these graphs for specific values of alpha. If you put alpha to be equal to 0.62, for instance, just an arbitrary number, you are not going to be able to find a graph for this one, operating characteristic curve for this one. And you have to do these calculations. But if you use some of the typical values, you can use these graphs. And also note that depending on one-sided or two-sided tests, these will also change. Actually, next I'm going to solve a question. I'm not going to solve a question related to one-sided. They're going to be pretty much similar formulation. Instead of z alpha over 2, it's going to be z alpha. Everything is else the same. But when we have, instead of normal distribution, if we have t distribution, let's see what's going to happen. When it comes to t distribution, employing t distribution, life becomes a little bit difficult. But I'd like to mention how t distribution is derived from normal and chi-square distribution. That's why I would like to talk about this. Now, actually, t distribution generally is represented by z plus m over in square root x squared divided by k. This is what we call t distribution with k degrees of freedom with m non-centrality parameter. Now, z here is standard normal distribution or distributed random variable, and here x square is chi-square distribution with k degrees of freedom. Now, if we apply this, let's see if we can obtain the t distribution that we know, which is actually x bar minus mu over s over square root of n. This is how we have defined t distribution. Let's see if we can obtain this result by putting these values here. So what we call as standard normal distribution is actually, in terms of a sample mean, is going to be x minus mu divided by population standard deviation over square root of n. Note that the reason why we use t distributions, we do not know the population variance. And x square is going to be chi-square random variable, and this chi-square random variable is going to be equal to k times, the way that we use is going to be k times s square over sigma square. There's one important point here. Z and x square should be independent from each other. This is basically, so this form is with that independence also assumption or constraint. This is how t distribution is formed. Anyway, so when we put these terms here, and let's assume that now mu is equal to 0. And when we put z there, we are going to see x bar minus mu divided by standard deviation of square root of n divided by x square is k s square over sigma square. Note that k is the degrees of freedom here. So instead of n minus 1, I have written k divided by k in square root. These will cancel, and this part is going to be s over square root, s over sample population standard deviation. Now these will cancel, this and will be here. Therefore, what we have would be equal to x bar minus mu standard deviation divided by square root of n, which is exactly how we have previously defined the t distribution. So actually, the t distribution that we know is this actually central t distribution. So the relation between what we call t distribution, central t distribution, and non-central t distribution is going to note that it's going to be t distribution with k degrees of freedom. There may be a non-centrality parameter. And here, when the alternative hypothesis is true for testing population mean, mu is not going to be equal to mu 0, then we are going to have that non-centrality parameter here. So how can we obtain that non-centrality parameter? Let's go a couple of more steps and see where this is going to lead to. So now we are going to be applying h is equal to mu is equal to mu 0, and h1 is mu is not equal to mu 0. Hypothesis test. And again, we divide the space into two. This is we conducting the hypothesis test. This is the other guy which actually who knows that actually mu is equal to mu 0 plus delta. So the way that we are going to be conducting the hypothesis test would be in this manner. T0 is going to be equal to x minus mu 0 plus. This is actually the real distribution. Okay, let me put it that way. It's going to be easier to understand. The way that we are going to be conducting is by this manner, mu 0. But actually, the other guy actually knows that this is x0 minus mu 0 plus delta here, plus delta divided by s square root of n. So now let's take this term, put it there, square root of n, x minus mu 0 plus delta plus square root of n delta divided by s. Let's go a couple of more steps. So let's divide both sides by population standard deviation. Now note that this part is actually equal to, as I've already shown you, is going to be x squared over k, chi-square random variable, divided by its degrees of freedom in square root. This part, if you take this and put it down here in the denominator of square root, as square root of n, this whole thing is going to be our z0, normal distributed, standard normal distributed random variable. Why is that so? Since actually it is mu 0 plus the delta is the actual population mean, this is going to be standard normal distributed. So this term is going to be actually equal to what we called here as m. So this is going to be basically t distributed random variable with k degrees of freedom with m non-centrality parameter, and therefore the non-centrality parameter is going to be equal to this. So in this hypothesis test that we apply, that t0 value will not be a central t, is not going to have a central t distribution anymore, but T0 is going to be distributed with k degrees of freedom and the corresponding non-centrality parameter. This is going to be the distribution of T0. So what's the big deal, you may say? Let me first talk about how the central T distribution and the non-central one looks like. This is actually our central T distribution. It is a symmetric distribution, but it is the tails are a little bit longer compared to population mean. And let me talk about why this is so, because it is to understand the skewness of the non-central distribution. Because the idea is we are estimating the S value here, the sample standard deviation. And note that the sigma value for standard normal distribution, that would be equal to 1, right? Because we are talking about Z, which is going to be normal 0, 1. But actually what we do is we are trying to estimate this one here. And in some cases, this may be severely or significantly, can be found to be significantly lower than 1. In those cases, when you divide x minus mu over s square root of n, this is determined to be pretty much smaller compared to 1, then this value is going to be pretty much high, or in absolute value. Therefore, we are going to be visiting more of these tails. That's why basically T distribution, the tails of the T distribution are longer compared to normal distribution. So normal distribution, if it's like this, right, this is going to be a typical T distribution. Now, what about non-central T distribution? In non-central T distribution, the mode is not going to be at 0. So depending on the sign of this delta, and let's assume that just like we did before, let's assume that it is greater than 0, then this is going to be shifted to this direction. However, that shifting is not going to be just copy and paste of this t distribution. It's going to be a skewed distribution. So if this is our central t distribution, then our non-central t distribution would look like this. So there is going to be a right skewness here. And as you go more, this is going to, again, right skewness is going to increase. And again, the idea comes from the S values when they are smaller. And now this time, since the mode here is shifted from a to a positive direction, a positive non-zero direction, therefore, if you have some small S values compared to 1, then they are going to be some extremely high values, or pretty much significantly high values here on the right hand side. And that's why this is going to be a long tail here. So that's why we have a non-central t distribution. So we are going to be sampling from this distribution if mu is equal to mu0 plus delta is the case, and we are conducting the hypothesis test using this statistic, because this is not going to be now around the mean of 0, and it's not going to be from a symmetric distribution. This distribution is going to be pretty much complicated. So using the same logic we have previously done, these were the, remember, these were the T alpha over 2k minus T alpha over 2k values, the lower and upper critical values. We are still going to be using these boundary values. And what was the type of error that we would commit here? If the value that we find, if the t value that we find, which is x bar minus mu over mu0 over s square root of n, if this value is here, then we would be committing a type 2 error, because actually h0 is wrong. This is not the distribution from which we are sampling. So we should find the area of this curve here. Note that this does not decay to 0 here. Between these 2 points, this one and this one. Actually, this very same logic that we have employed in normal distribution. So that would be the area of type 1 error. I'm sorry, type 2 error. So that area would be equal to beta, which is type 2 error probability. So this area would be equal to beta of probability that T0, let's call our now new distribution T0 prime, right? The non-central T distribution. This is going to be smaller than T alpha over 2 K degrees of freedom, where T0 is the non-central T distribution with, what was the parameter? Square root of n divided by standard deviation. Now, it is not easy. Actually, you need numerical integration to compute these values. Therefore, in order to bypass this, what we do is we use our these operation characteristic curves. Here, there's actually an example I have pasted here. And the way to use this is similar to what we have done previously for the normal distribution case. If we go back to the normal distribution case example, we had this example here. And I said that we know the standard deviation, population standard deviation, and we suspect that, or we would like to detect a change of 1 centimeter per second in population mean. What should be the sample size to detect this much of a shift in population mean with a power of 0.90 or 90%? That was basically the question. We may ask actually a very similar question, but this time this information would not be given to us. So we are still talking about the same example, but the population mean is not known. A population standard deviation is not so. So this is the test we would like to conduct. And we would like to conduct this test at 0.05 significance level. This is the type 1 error that we would like to commit at most. Then the question is, what should be the sample size, but again with a certain information, the additional constraint that we need to apply, which is related with the population mean. Now, there is unfortunately a difference between the application in t-distribution case. When I write here, I would like to detect a change of 1 centimeter per second, right? Now, what I need to define here is that non-central parameter is dependent on square root of n, which is no big deal actually. It can be found by trial and error, but the problem is we do not know this population standard deviation value. One thing that you can do is you can take a small sample size, let's say you collect 10 elements, and estimate the population standard deviation by a sample standard deviation here. That may be one case. And note that it's going to be bias estimator, and you can correct it for bias as I explained in some other bonus video. But you don't need to do that always. In most of the cases, we are not interested in a change of not interested in a change of mu values in absolute values, but we are interested in terms of sigma values. How much sigma values are we going to allow, or are we going to limit ourselves so that we can detect the change? So what I say is, as I said previously, we are much more interested in that value. So we may say that this alpha over sigma value, which is the effect size, we would like to detect this, for instance, a 0.5 of effect size. We would like to detect this with a power of 0.90. So in this case, we are going to allow for a type 2 error of 0.10. So now the question is more clear. With this constraint at hand, but note that this constraint simply is not going to say anything about the absolute values of the in terms of x or mu. It's going to be a description in terms of standard deviation. So we allow, or actually we limit ourselves in detecting, or we would like to detect a change of 0.5 times standard deviation in population mean. What should be the sampling size? So we use the related table from your textbook. We need to define, for instance, as I already said, for normal distribution, we need to define the alpha value. Hopefully it's already defined. And now we need to define D here, right? D is the effect size has been taken as 0.5 again. This is our 0.5. And we would like to determine a change here with the effect size of 0.5 with a type 2 error of 0.10. All right, it is somewhere here. And this value is going to be, again, if I just concentrate on this value, which is not going to be very much easy. All right, it's going to be somewhere like 50. So 50 observations would be about to be sufficient to obtain a power of this test to be equal to 0.90. Now, if you compare it with the case related with normal distribution, that value with the same effect size that was equal to 42 that we have found, and using the graph we have found it to be 40. When it comes to t-distribution, it is 50. Note that this is also for two-sided t-test. So for each type of test at a different significance level, we have another of these operating characteristic curves. Okay, so the sample size has slightly increased, of course, as you should expect from t-distribution. So I'm not going to go into chi-square distribution and other distributions, but this is how generally we can use how we can use the power of a test with the effect size to determine the required sample size to obtain that power.